Okay. Now that we have the wave equation, let's see how we can solve it. So let's start with one-dimensional wave equation solution. Okay. Okay. Let's first start with the what's called a progressive wave solution. The pressure expressed by this second-order differential equation can have two solutions. Okay, where we have u ct minus x and v is equal to ct plus x. U and v are constants, and what that means is the shape doesn't change as it propagates. So if they're constants, then we say du over dt, du over dt what this is suggesting to us that wave is traveling with a speed of sound c in the positive direction. And if you apply the same approach to the other solution, then we have a wave that's propagating in the opposite direction, again with the same speed of sound. Okay, so such waves, what it says is it has a component that propagates in positive x and negative x direction, and the wave speed is equal to c. Now, for periodic waves, we can write these as, let's see. Okay. What we have done is insert omega here, and k over omega, k is equal to omega over c. It's called, let me just express this, it's called the wave number. Okay, and lambda is the wavelength. F is the frequency. And wave equation solution for periodic waves can be written in exactly the same form, same argument, in this case cosine omega t minus kx plus cosine omega t plus kx. That expression can also be written in complex form. Okay. Remember, I is square root of -1, the complex shape. When you write it in a complex form like this, the actual pressure is the real part of complex pressure now. These expressions satisfy the wave equation that we wrote at the very top. At the very top, del square p. So this equation, wave equation, is satisfied by these expressions. So if you just substitute for pressure, you will get an equality on both sides. Okay, that's one. The relationship between pressure and particle velocity. And where does this come from? This is a very simple quiz. Where does it come from? Just a moment ago, I mentioned to you the continuity and the force equation. Exactly, right? Just a moment ago. So if pressure can be in one direction, actually, let me take this opportunity and express a couple of things here. This same expression can be written as this, correct? And what we have here is, this description is a periodic change with x. Its real part is cosine kx. So it's a change in space. If you were to freeze the pressure propagation in space, you look at this wave change, that's what the expression would be. Whereas the first one is in time. So if you're measuring pressure at a given location as it propagates, it will fluctuate as a cosine omega t with a frequency omega. K here is wave number, but it's a spatial frequency. Okay? So it shows how it changes over space. Now, the particle velocity was related to the pressure through acceleration, right? If you remember, it was rho times del u del t was equal to del p del x, meaning the gradient of pressure in one dimension is equal to the density times acceleration of particle velocity in the same direction. Now, if pressure, I will do these because very simple. If pressure is expressed as such, del p over del x is from here, ik a e to the minus I. So it's, okay, ik times itself. Now, on the other hand, the particle acceleration will have the same form and minus I omega t ux. So if we substitute both of these, can we simplify this further? Of course. Remember, wave number is radial frequency divided by the speed of sound. So what we have is but this is true only for plane waves, this simplification. Pressure and particle velocity are related through a product of density and speed of sound. Let's take a look at this expression a little bit more. What is it? What's the ratio? Oh, then you don't have an answer. Okay. What is this expression? Exactly. Impedance. Pressure over particle velocity. So we call this the impedance. But this is a point impedance, or we also call it specific acoustic impedance. So for a plane wave, the acoustic impedance is a constant, rho times c, as simple as that, okay? For a plane wave only. And the value of that is, let's see now, kilogram per meter square times second. So we're still on the topic of impedance. While we have that, we have something called, let me put it here, mechanical impedance, because these will come in when we start looking at vibrating systems, pistons, etc. And what's a mechanical impedance? Let's call it Z sub m. That would be force divided by velocity. And that would be kilogram per second. In general, acoustic impedance would be sound pressure divided by volume velocity. And that would be a kilogram meter per second. Okay, so these are three definitions of impedance that we use: specific acoustic impedance for plane waves, and mechanical impedance for mechanical systems, and acoustic impedance where it is defined as sound pressure over volume. Impedance in general, let's call it radiation impedance in general, is a complex number. okay, in general, complex and frequency dependent. Okay, not like for plane waves as we had z is equal to rho c. Okay, for plane waves it's simple. It's constant, it doesn't depend on frequency, and it's real. But in general terms, that's not the case. And we mark it as z of omega, and it's defined as the ratio of pressure to the velocity, normal velocity, at that point. And that ratio has a real part and an imaginary part. Often, okay, this is the impedance. Often we also use a term called acoustic admittance associated with a surface. Okay, acoustic admittance, and that we define as beta, a frequency-dependent number that's inverse of the normalized impedance. Inverse of the normalized impedance. Let me put it up here. Okay. And it has a real part and an imaginary part. The expression for the real part, xi, can be obtained from the real part and imaginary part of the impedance, and we do call this the acoustic conductance of a surface. Okay, acoustic conductance of a surface. And sigma, okay, that's the imaginary part of the admittance, is the corresponding value. And this is called the acoustic susceptance. You don't necessarily need to memorize these day and night, but it's good to know what they mean, where they are, because these are sometimes the values given to characterize materials, okay? When you characterize a material, how much resistance will it show to sound waves, or how much absorption will it have? We need to use these terminologies to characterize them. Any questions on these? We're still under learning mode. We haven't started applying yet. We will before the day ends, okay? Soon enough. Now, one other thing, energy in a plane wave. Because after all, waves, primary function of waves is carrying energy. So how do we find the energy in a plane wave? Once again, we consider the small element in the fluid or gas. And the kinetic energy, of the a small element would be, of course, its mass times velocity. So okay, that would be the mass, and expressing the velocity in terms of its displacement. We can also density, elemental volume, and square of the particle velocity. Now, what about the potential energy? Potential energy, again, if you consider the same elemental volume, is proportional to how much you're able to squeeze, much like a spring, okay? If you squeeze it or if you pull it, how much energy can you store in that system? So if we use a negative sign, if we change its volume from ambient volume to something smaller, pressure times that change is basically what gives us its integral is what gives us the potential energy. Now, from continuity equation, we have mass continuity. Okay, density times volume will not change. Density times volume. Now, if we substitute for density at any times with the changes, and expanding it, this is a very, very small number, okay, higher order term, because 2 perturbations multiplied is negligible compared to the other ones. Of course, these are same on both sides. So we essentially end up with an expression for volume change in terms of density change from the ambient values. Just to remind you, the subscript 0 refer to the average constant values, okay, when there is no perturbation. From earlier developments, we have and that was the change, if you remember, change in density, which we can write as change in density is proportional to change in pressure through square of speed of sound. So substituting back here, and finally substituting in this expression and integrating it, okay, we end up with 1/2 1/2 So we have kinetic energy, we have the potential energy, and the total energy in the system will be their sum. And that we can write as and one expression that I'd like to add here is energy density. That would be per volume element. Okay. That means dividing it by V0, and that okay, I think we're done with derivations, and we're going to move into how sound waves are used, how they're related to various interactions, and so on. Now I'm going to start asking you questions about how we use sound waves, okay? In just a moment. Any questions so far? Is there anything that's complicated? What I would do if I were you is, after class, go over some of these derivations, see if you're able to follow and make sure that everything makes sense. If not, just either send me an email and we can talk about it before next class. Don't wait until next class. Or if you have to, we can talk about it then also. Okay? Now, a slightly new topic. Now we want to talk about reflections and transmission. One-dimensional plane waves, and normal incidence. I'll explain all these. Okay. Let's say, like I had shown in the schematic earlier, you have some sort of an obstruction, let's say a wall, okay? And sound waves, the wave fronts are propagating towards it. What will happen naturally is waves will arrive at the wall, and then some will be reflected and some will go through. And some of those that go through will be absorbed by the wall, if it can be, and some will transmit to the other side. Right now, the first thing we are going to do is look at very extreme boundary conditions, meaning this is either perfectly rigid or perfectly vacuum. And I'll get to it in a moment. The key here that will help you to establish at the very beginning is how to express pressure waves. So if a sound pressure wave is going in this direction, how would you write it? What is the expression for it? I say, okay, write down the sound wave expression for the sound that's incident on the wall here. Okay, P equals what? Okay, remember we solved the equation a moment ago. See these? These are the sound wave solutions. Okay? This plus minus indicates which direction it goes. So if we take x here as positive, what we want to do is take from here sound pressure, take an amplitude I, okay? We have a harmonic change in time, it must have, and also propagation. That is essentially the pressure wave that's traveling in the positive x direction. And usually, for ease, we write it as this. The subscript I means incidence. It's incident on the wall. Well, we said that when it interacts with the wall, some of it is reflected back. How does one write that equation, that expression for pressure? See, some of the sound now is going to be reflected back. Yes? Come on. Say it. Say it. Yeah. You both have beards. So. Okay, do you know? Come on. You can do this. No, but add what up? What's the second one? How do you write the second one? This is still incident. Now we have to write this. This is very simple.
Plus case.
Say again?
The same expression with plus case.
Plus case. Okay. Reflection, not exactly. A different amplitude. That's important. Time is not, frequency is not going to change, but this will change. Minus, minus, now it is in the negative x direction. Okay? So now you have an incident sound pressure and a reflected sound pressure. In front of this wall, the acoustic field is described by a sum of both. I think this is what you were saying. Okay, you add them. This is the total sound pressure. And if you do that, then you have okay. Now let's take the case of a rigid surface. What happens at a rigid surface? Exactly. Particle velocity is zero. That's the boundary condition. Okay? Rigid surface means particle velocity vanishes because it's a rigid surface. And that means ux is equal to 0. And if you remember, we were able to write a moment ago, there was a reason why we expressed it, del P over del X. Okay. Okay. This is the expression for particle velocity that we had derived just a few minutes ago. If you look here and take the derivative of the particle del P over del X, the pressure with respect to space, what you end up with is IK um, okay. This is common on both sides, and evaluate this at x0. You have 1 over rho c a minus b, because particle velocity at the surface is 0, and this then suggests that the amplitudes of incident and reflected waves are exactly the same. If we define a pressure reflection coefficient, okay. Okay. Just briefly, what we have done is we wrote a general expression for a normal incidence plane wave. Okay. What normal incidence means is plane waves are parallel, wave fronts are parallel to the wall. They don't go at an angle, so they reflect off angle. Okay. So we wrote an expression, incident pressure, and then we wrote a general expression for the reflected wave. The two things that are important, one is we don't know the amplitude of the reflected wave, but we know that frequency has to be the same, because there's no mechanism here that would change the frequency. So the total sound pressure in front of the wall would be equal to their sum. Now, one thing we do know is if this is a rigid surface, particle velocity will be 0. But we know from just a few minutes earlier that particle velocity is related to the sound pressure. What did we say? The density times the acceleration of particle is equal to the negative of the pressure change, del P del X. So if you make that substitution and take the sound pressure derivative with respect to X, and you end up with the condition that incident and reflected waves must be the same. And their reflection coefficient, pressure reflection coefficient, is equal to 1. So if we go back and substitute in the total sound pressure expression, what we end up with is there's a common mistake here, this sign and this sign, okay? This sound pressure, this is because of the derivative with respect to x, okay? That's why it becomes as negative. And so, and you can see here, by dividing this 2 and multiplying, we have 2a now. What does this tell us? This tells us that if this is x equals to 0, the amplitude of the sound wave is twice as much as the amplitude of the incident sound wave. Okay, x0, this is 1, so you have 2a. Now, as you go away from the surface, okay, cosine kx, at some point, at some point, what will be a nodal line. What you have is an incident wave and a reflected wave building up an acoustic field. And if you have a microphone that you move from the surface, okay, a certain distance away, theoretically you'll get zero, okay, because of the destructive interference of the two pressure waves. And then it will increase again and it will decrease. Okay. What will that show us? Okay, this distance n plus 1 over k is 2 pi over lambda. So lambda over 2 pi. Oops. From here, you can actually measure the wave, get the wavelength information. Let me describe this one more time. If you had a, this will become more clear as to why we do this later on. But what we're saying here is, if you have a microphone on the wall, if it's a rigid wall, you'll have twice the pressure amplitude. And as you move from it, you'll come to a point that will give you a zero pressure. Okay, that's a nodal point, node, just zero amplitude. Now, if on the other hand, and we will do it in a moment, if this were vacuum on this side, say there's a membrane that's protecting, what would be the pressure at the boundary? It would be zero. And as you move the microphone, it will come up to a maximum. Okay. And you don't have to write this. I just want you to think about this for a moment. Vacuum doesn't have to be always, this could be water and this could be air. The difference is such that it's also a zero pressure, basically, okay, at the surface. Now, what if the condition is something in between? It's neither rigid nor vacuum, but something in between. Then this is going to be neither zero nor the maximum. It's going to be somewhere in between. And by making these measurements as you go away, and I will get to it, so again, don't write it yet. By making these sound pressure measurements, you can actually determine the impedance properties of materials. Okay? That's why we're now looking at these extreme and simple cases, and we'll build up to more complicated cases as to how you can, just by measuring sound pressure changes, understand the material properties of the surfaces. Okay, let me just go to the second, well, let me just continue on this just for a moment first. The particle velocity, we said we have the sound pressure. This was the sound pressure. Again, we're continuing on the rigid surface. What would be the corresponding expression for particle velocity? Okay, why don't you take 2 seconds and see if you can write the expression somewhere on the side. What is the particle velocity? See if you can do it quickly. You have all the information in front of you. Do you have it?
It's 1 over omega c times p.
Mm-hmm. Well, it's very...
Rho c.
Okay, yes. It's very, very similar, right? 1 over rho c. But there's a change in the phase, and that's expressed through the sine cosine differences. Okay, and so this will be the particle velocity, and the real solution, because these are complex values, for pressure would be 2a cosine kx cosine omega t plus some phase angle. And of course, particle velocity, the real would be now only the difference between this phase, impedance, and now, I want to complete this notion one more time. If you look at just the spatial aspects of this, okay, pressure at x equals a, pressure becomes 2a. Okay, and at x equals, well, let's find out where. To make cosine kx 0, kx the first time would be pi over 2, and k is okay. So pressure is 0. When you are a quarter of a wavelength away from the surface, okay? And as you go, and you can calculate it at 3 lambda over 4, it will be 0 again, and maximum here, maximum there. Okay, these are the relationships with distance. Let me do a quick derivation for the pressure release or a resilient boundary. Okay. Now we did the rigid surface or rigid boundary. Now let's do a resilient, or in acoustics terminology, pressure release boundary. What does this mean? Let's say this is where the acoustic medium is, sound pressure goes and comes back. This other side is theoretically vacuum, or its density and speed of sound is so much less, than the left-hand side that you can assume it to be almost a vacuum. Now this condition is similar to having water on the side and air on the other side, okay? It's almost like vacuum. The key point here is the boundary condition. As always, whenever you're solving these wave equations, you need to be able to define the boundary conditions. In fact, I will say something here, then I will keep on reminding you for the rest of your profession that I said so. Boundary conditions in acoustics is one of the most difficult things to determine, okay? That is, when pressure is incident on a surface, how much will be reflected. In automobiles, for example, they're modeling the interior of a car. Okay, we have all these very nice, fancy software systems, but boundary conditions are always the most difficult part. We do not know. They're always empirical. We try various values and numbers. So that's why it is important to have a good feeling, good understanding of what boundary conditions are. In this case, we covered one extreme case, perfectly rigid. There's no such thing, of course, perfectly rigid. And this is the opposite, perfectly resilient, meaning pressure release. So what would be the boundary condition here? In the other one, we said rigid, meaning particle on the surface doesn't move. What is the boundary condition here?
Velocity doesn't change. Particle velocity.
But particle velocity doesn't change. What does that mean? Can you say it differently?
In the other case, ux was 0.
Mm-hmm. Yes.
And here ux is pressure will be 0.
Pressure will be 0. That means particle velocity doesn't also change. Okay? Same idea. Pressure is 0. So pressure is 0 at this point. And that's same idea as before. So we once again, we are able to write a e to the minus I omega t for the incident, and for the reflected, you can say, and the total pressure is their sum. Now we are saying that at the surface, they should be 0. And if we do that, what can you write about it at the surface? A plus B is equal to 0, basically. And what is the pressure reflection coefficient?
Minus.
Exactly, -1. So substituting back into the total expression here, we will now end up with divide and corresponding particle velocity, of course, will be 2a over rho c cosine kx. Now, let's look at this one more time. The pressure on the surface is 0, right? When x is equal to kx is 0. When does it reach a maximum value? When kx is equal to pi over 2. Correct? And just like the other, but in the opposite, at lambda over 4, pressure is maximum, quarter of a wavelength away from the surface. Okay. Any questions? Yes.
I couldn't read the condition you wrote for the vacuum.
Oh yes, sorry. Okay. If you take the density and speed of sound of one, and let's say density and speed of sound of the other, if rho E CE is much, much less than rho C, you could assume it to be a pressure release boundary. That's all. Any other questions? Okay. Now, in the next unit, what we will do is talk about what happens to sound waves as they move from one medium to the other. Let's say from air to water or from one fluid to the other one. Okay.